Okay. So today we are going to talk about Lab 3, which you are going to work on. You are going to do next week, next Tuesday. Okay. And the focus of Lab 3 is essentially going to be on the analysis, a numerical analysis on airfoil and effects of changing contact angle of attack in airfoil design, airfoil characteristics, parameters like lift coefficient and drag coefficient, and so on and so forth. And the means to do so, we actually are going to use a very old software called Xfoil. The good thing about this software is that it is free, first of all, right? It uses panel theory. So essentially, and which is very quick, not very comprehensive, but it is very quick. So essentially, if you were to design an airfoil, if you wanted to see if an airfoil is usable, is applicable to your design, you can just quickly test it in this software, using this software, get the results in like 30 seconds, and then continue with your design, right? But it is not going to give you a like comprehensive CFD analysis of an airfoil. That makes sense. So that is going to be the focus of today's lecture. And before that, we want to talk about wing design and the wing geometry a little bit, a little bit of theory behind the wing design in general. And then we will talk about the Xfoil software. Okay. So when you want to design a wing, you have to be mindful of its performance, its stability, and control. Also, manufacturability plays an important role, operation cost, and flight safety. So these are the main parameters that you have to be mindful of. But we are going to focus on two things. Performance first, which means that when you're dealing with the performance of a wing, it essentially means that you are talking about the stall speed, the maximum speed, takeoff, run, range, and endurance of an airplane using a specific wing or a specific airfoil. And we also are going to talk about the stability and control of a wing or an airfoil. And the main parameters there, the main thing that you want to talk about is the lateral directional static stability, lateral directional dynamic stability, and the aircraft controllability during the wing itself. Okay. So you have learned about the theory of the stall condition, the maximum speed of a wing, and all of those things in your aerodynamics course in AESP 265. But the rest of it, like the range, endurance, and the stability part, you will learn in AESP 420, which is flight dynamics and control, flight mechanics, flight and orbital mechanics, and also another course, flight dynamics and control. But we will see a very brief introduction to all of those things. Is there any questions so far? Okay. Well, what are the parameters that we are working with when we want to control the stability, change the stability or the performance, and enhance the stability and performance of a wing? The first parameter you want to work with is the wing planform area and the number of wings. Essentially, your wing area, right? The second one that you can play with is the vertical and horizontal position of the wing relative to your fuselage. The third one is the cross section of the wing, which is your airfoil, right? And the other ones are the aspect ratio of the wing, the taper ratio, tip chord, root chord, MAC or mean aerodynamic chord, and span of the wing. We also have the twist angle and the swoop angle to play with. Also the dihedral angle and incidence, the angle of incidence. You can also, after changing all of these parameters and coming coming with a very good solution for your wing design, you can also add high lifting devices such as flaps and other like high lifting devices. Is there any questions so far? Okay. But the main question is, what is going to be your design goal, your design principle when designing a wing? And that is a question I have for you guys. What do you think? Huh?
I think it depends on the mission of the plane.
Okay, can you elaborate?
Like if you'd want to go for long distance sustained flight, you design your wing differently than if you were designing something that's achieving like its main goal speed.
Okay. How would you represent that design goal? What is the parameter that you need to play with?
Like, I suppose like the shape and orientation as far as like sweep and stuff like that of the wing. Like you wouldn't put a delta wing on a liner.
On a commercial airplane. Okay.
Yeah, but you wouldn't want a glider wing on a fighter.
Okay. Okay. Do you have anything to add?
You want less weight and more lift. What's the mission for a high-speed aircraft?
That's the mission for any aircraft, essentially, right? You want more lift. Higher speed aircraft, you want more thrust, right? That's the idea. But the thing is, do you have anything to add, Igor? The thing is, you're correct. All of you are correct. You're not wrong. But eventually, the main goal of an aircraft is to float in air, right? And how would you do that? You control the lift to drag ratio, right? You want to maximize the lift to drag ratio. If you have the maximum lift to drag ratio, essentially what you're going to have is that you're going to require the smallest amount of power to keep the aircraft in the air, right? That's the idea. So this is going to be your main design principle. And then the stability part, the performance part, the maneuverability part come in later, right? As you mentioned. So if you wanted to come with a flowchart for your wing design, the first thing you need to do is to select the wing geometry, like the aspect ratio, and all of the other parameters, then add a high lift device if you need a high lift device, then select the airfoil you want to use in your wing or the number of airfoils. You can have different airfoils actually on the same wing. Based on that airfoil, determine the wing parameters. Again, like a trial and error, if you will, and then calculate your lift to drag ratio, right? See if it's an optimized ratio for your design or not. If you want to change it, if it satisfies your requirements, just optimize, finalize your design, and you're good to go. If not, then you have to redo the whole thing again and again and again until it satisfies your requirements. Okay? But what is our final goal here? Our final goal here is understanding the design of a wing, of an airfoil essentially, and the importance of different flight parameters. I mean, the only flight parameter we get to play with in this specific lab is the shape of the airfoil, like the different airfoil that you're going to use. But you have changed flight parameters in your other two labs, right? And you have seen, I assume you have seen the effects of changing, like, what did you change in the lab?
I changed the length of the wings.
Length of the wing. Did you see the effect of that change? What about you?
I don't remember what I changed. I changed the sweep of the wings.
Okay. Did you see the effect of that?
A little bit, but I didn't do like a drastic angle.
Okay.
It wasn't that much different.
That makes sense. That's what I expected. You shouldn't have seen that much of an effect on a Cessna aircraft.
I just increased the surface area of the lift surfaces.
Okay. And did you see any?
The
lift coefficient and the drag coefficient both increase since both use surface area and the common
But did you see the effect when you were
Oh, yeah.
flying?
Oh yeah.
Okay. So what was the effect?
The lift and drag ratio still increased, so I was able to it was a lot more sensitive, and I was able to barrel roll and
Okay.
So I changed the volume of the fuselage, and what I noticed was I was getting too much lift. I would always pitch upward, and so I tried landing it, bounced up, and then it crashed, and that's what happened.
So essentially, what you're telling me is that you lost a lot of stability, right?
Yeah, no stability, a lot less drag. It was basically I always wanted to fly up.
Okay. Okay. So you have seen the effects of this changing this design parameters, but then the next is in this lab, in the upcoming lab, you get to change a different airfoil. You get to see the effects of different angles of attack on different airfoils, and you get to analyze them and write a report, of course, and propose potential improvements, if you will. These are the final goals of the lab. Are we clear? Are you guys clear on what to do for the lab? What is the final thing I want from you guys in this course?
For the next lab?
No.
overall.
Like the final submission.
Design our own aircraft.
Essentially, I mean, if you do design your own aircraft from scratch, you'll get a lot of bonus points. But essentially, what I want from you guys is to take one of the aircraft that are already available in the flight simulator we have and change a lot of things about it, not just one parameter. So essentially, designing a new aircraft, right? And then, like, being able to justify the changes. Why did you change this, right? And being able to fly and land it essentially. Okay, so that's the final goal of the lab. I just wanted to make sure we're on the same page. But moving on, the theory, the four main aerodynamic forces that are going to be applied to your aircraft are the lift, thrust, weight, and drag. So in this lecture, and in your aerodynamics in general, we are going to focus on lift and drag, right? Because your airfoil, the shape of the wing, the airfoil, and the type of the airfoil you use is essentially going to affect lift to drag ratio, right? Thrust is controlled by your engine, and weight, it's very obvious, right? It is controlled by the material and the type of design you're using. I'm pretty sure most of the theory you should have seen in your aerodynamics. If not, you can always ask your questions if you felt like you don't know the material. Okay. So let's talk about the airfoil geometry and the nomenclature of the airfoils. Airfoil is a two-dimensional cross-section of your wing, which is supposed to create sufficient lift with minimal drag. And as I've mentioned, your design target is to maximize the ratio of lift to drag. The nomenclature we're going to use on the airfoil are listed here. We have the leading edge, which is the first point that your airfoil meets the air, essentially. And you have the trailing edge, where the air leaves your airfoil. We have the chord line, which is the smallest distance between the leading edge and the trailing edge. We have the camber, mean camber line, which essentially means that each point of this line has the same distance from the top and bottom of the aircraft. And we also, the distance between your chord line and the mean camber line is called the camber. If your camber is 0, then you are dealing with symmetric airfoil. Okay. I assume you're already familiar with the angle of attack and thickness of the airfoil. Is there any questions so far? No. Okay. But what are the aerodynamic forces and moments being applied to your aircraft. So we essentially have a normal force on your airfoil, which is the pressure force type, and we also have the tangential force, which is the shear force type, right? These are the two main types of forces that are being applied to your aircraft, right? These are the two main aerodynamic forces that are being applied to the surface of the wing, okay? And if you look at each point of the aircraft, it can represent all of the combination of the surface force and the shear forces with a moment and a resultant force, R. Okay. Okay. So the sum of forces due to pressure distribution and the skin friction can be represented like this. This is going to be your shear stress distribution. It's going to be your pressure distribution. You have to keep in mind that your pressure on top of the airfoil is always negative, and the bottom it is always positive. Okay. So let me ask you this. Let me tell you this first. And we can actually have two components. We can make it into two components. The forces that are being applied to your airfoil, lift and drag. You have to keep in mind that lift and drag are the components normal and tangential to the flow direction, respectively, right? You can actually work with the force components that are normal and tangential to your chord line. Those are going to be called differently. I assume you have seen those forces in your aerodynamics, right? Okay. But the main forces we are going to deal with are the lift and drag, which are normal and tangential to the flow. Yes.
We'll be looking at the stagnation points and airfoils and exfoils.
Stagnation points. We are not going to focus on the stagnation points. Why?
Just because it would relate to the whole lift and drag forces.
How would you relate the stagnation point to lift and drag?
Depending on your angle of attack, where your stagnation points, you can have different variation in lift or drag. So you could represent an exfoil showing.
But you essentially are relating lift and drag to the angle of attack, right?
Right.
Because your stagnation point changes because of the changes in angle of attack. So angle of attack is the main parameter there, right?
Okay.
Right? Just the stagnation point is just a mediating parameter, right?
Mm-hmm.
Okay, so we are going to see the relationship between lift and drag and the angle of attack, which are the most common parameters used in this type of analysis. But let me ask you this. What is the main mechanism? And I usually ask this in my aerodynamics classes, in the 500 level class. I'm pretty sure you know the answer. You should know the answer as like junior aerospace engineering students. What is the main reason behind the lift?
Pressure.
Okay. Can you elaborate?
I don't remember which direction, but I think high pressure was on top of the wing and low pressure is below. Those might be vice versa.
It's either way.
The other way. It is exactly the other way around, right? As you can see from that distribution. Because if the high pressure was on top and low pressure was on bottom, then you were pushing your wing down, right? But lift is pushing your wing up. So the pressure difference, yes.
Low is on top and high is on bottom.
Let me put this, you have negative pressure distribution on top and positive pressure distribution on the bottom. Okay, so that's a more accurate description. Okay, that's good. One very important parameter in airfoil analysis is the center of pressure. Is there anyone who can tell me what the center of pressure is?
Wouldn't it be where there's like the mean pressure distribution of all surfaces on the aircraft in relation to its physical body?
Mean pressure distribution. But like mean pressure distribution is an arbitrary thing, right? Like you take the like you add all of the pressures to locate it on one point, right? Does it make sense? But in reality, it is always a distribution, right? So, but the center of pressure has a specific characteristics, and it's a real thing, like the center of gravity.
I know it's related to the center of gravity. Like they have to be in a certain relation to each other to have like
Yeah, then exactly, and you're gonna see that later in the fluid and orbital mechanics course. Yeah. Center of pressure. What is the most important? What is the definition of the center of pressure? It is, of course, it is related to how the forces are being applied, how the forces are acting actually at that specific point, right?
At the center of pressure, that's where there's not much flow, right?
Not much flow.
Flow is on the boundary layers mostly, and then in the center, it's mostly stable.
Center of pressure is inside your wing, right? So there's no flow. It's just a solid thing.
Is it where the normal forces from the top part of the airfoil and the bottom part cancel each other out?
You are on the right track, right? So we have there is something about forces canceling each other out, but not the top and bottom forces. Let's go back here. If you look at this, the resultant forces, we are talking about the resultant force and the resultant momentum, of course, right? At each point, you have a distribution, like the force here is applying a momentum here, right? And the force here is applying a momentum here in the other direction, right? So if you were to summarize the forces at a specific point, we have to represent them with a moment and a resultant force that has two components. But we only talk about lift and drag. We don't talk about the moments, right? What has happened to the moments? That is directly related to the definition of center of pressure.
So the first moment, when you get shear.
Pardon me?
First moment, you said it was in lift, center of lift was, center of pressure was in the wing.
Center of pressure is inside here, right? Do you think this force applying a moment in this location?
So yeah, do you get shear out of that?
Pardon me?
So you have shear forces too, right?
You have shear forces too, and they are applying moments on any point actually, right? You have shear forces, you have a combination of shear forces because of the viscous effects, because of the bilayer dimension, and also pressure forces that are there because of the pressure difference between top and bottom of the airfoil. Okay, so again, if we want to be accurate in our resultant force representation, if you will, we have to represent every force with a moment as well. But we don't do that. We only deal with lift and drag. And this is directly related to the definition of center of pressure. Let me actually see if I can help you here a little bit. Right? So let's say we are looking at this point here, and we are only looking at the shear forces. Is the shear force at this point? What is the direction of moment it is applying at this point?
Clockwise.
Exactly. What is the direction of this one? The shear force at the bottom.
It's counterclockwise.
Counterclockwise. So it is possible for them to cancel each other, right? And so it is possible for the moments, right, to cancel each other at that specific point. Okay. So it is possible for us to find a specific point on which all the moments cancel each other out. So the moment is zero. And you can essentially represent all the forces that are being applied on your aircraft with two forces. One force in the normal direction, one force in the tangential direction, because the resultant moment is going to be 0. Right? Does it make sense?
So is that the moment from every location on the wing?
Exactly. So the moments from all of the locations on the thing, if you just sum them up, you'll get 0, right? And that location is called the center of pressure. Okay? Center of pressure is the point on your airfoil, the body, inside your body. It's usually inside the body, inside the airfoil. About which the aerodynamic moments, the summation of the aerodynamic moments are going to be 0. So you can essentially, at that specific location, you can represent the resultant forces with just like just one force without any moments, which has 2 components, lift and drag. Okay? So that's the idea. At the center of pressure, there is no moment, so we have only one resultant force, which has 2 components when you compare it to the flow direction. Lift and drag. Okay. So before moving on, let me ask you this. Is there anyone who can tell me what is the aerodynamic center? Do you remember it from your aerodynamics? Does this name ring a bell? Yes, so you have heard in your aerodynamics.
Is this where the wing is naturally at rest and when dealing with the free stream velocity?
What does naturally at rest mean?
Where it stabilizes itself with no external inputs. It just kind of, it's like if you put a rudder in a stream and it finds its way to where it's just going to be stable. Is that where it's like balanced?
So that location is a location where the wing is balanced. But that's a point. Aerodynamic center is a point on your wing, right?
Is that where the rotation is 0? Because I do remember in aerodynamics we were talking about rotation.
Rotation.
Something that...
The only rotating force you have here is the moment, right? And if the summation of moment is 0, then you are dealing with center of pressure.
So the aerodynamic center, is that where there's the rotation of the flow is 0? There's no flow there?
No. So the aerodynamic center is actually the location where the resultant moment, doesn't change with angle of attack. Okay? And that's a very important location because you can represent your lift and drag there, right? For each angle of attack. But center of pressure changes with the angle of attack. Like for subsonic flows, that aerodynamic center location is usually located as, for different airfoils for everything, is usually located as quarter chord. That's why the quarter chord location is very popular, because it's where the aerodynamic center is in subsonic flow. When you move to supersonic, it moves closer to the half chord. Okay? So let's talk about the coefficients. We have a lot of coefficients that we talk about in aerodynamics in general, right? We have the dynamic pressure, which is 1/2 your free stream density and free stream velocity squared. Then we have the lift coefficient, which is your lift force divided by your dynamic pressure multiplied by the platform area. And that's actually the definition of any coefficient. Let's say when you want to find the drag coefficient, you have to divide the drag force by the dynamic pressure multiplied by the platform area. Normal force coefficient, normal force, dynamic pressure divided by platform area. Axial force coefficient, the axial force divided by dynamic pressure multiplied by the platform area. But when you're dealing with the moments coefficient, you of course have to include an R, because in your moment calculation, moment is force multiplied by the distance, right? An R. So for the dimensions to be consistent, you have to do dynamic pressure multiplied by the platform area multiplied by the length. And we also can find the pressure coefficient and the skin friction coefficient. which are essentially pressure force divided by the dynamic pressure multiplied by the planform area. But the pressure force is the pressure difference multiplied by area itself. So you can just take the areas out for both cases. That's why the formula is a little different, because we can't simplify it. Is there any questions here?
On the moment equation, is that Q infinite times SL?
SL, yep.
So what is it dividing your like lift, drag, axial, and moment and all that, dividing it by Q infinite S? What does that actually like do to the values? Does it normalize it, or?
It does normalize it. That's the, so essentially you want to find a non-dimensional parameter that you can use to compare different things, right? That was the idea behind non-dimensionalization, right? You want to use it to be able to scale your design, to like compare different designs. This coefficient is a non-dimensional value. Okay. Of course, when you are dealing with an airfoil, you are dealing with a two-dimensional case. In a two-dimensional case, a planform area is essentially going to be your chord length multiplied by a unit depth, right? So your S, which was the planform area, or the wing area, is your chord multiplied by 1, for example. So your coefficients are going to look a little different. Your lift will become lift per unit area, right? Because it is not a ton, like it is going to be applied on just one, on a line instead of area. Your drag and moment are going to be drag and moment per unit area as well. Okay. Does this make sense? Pretty sure you have seen this before. I use the same slide as Dr. Farag for these things, so you should have seen this exact same slide. Yeah. Okay. Any questions? No? Okay. So let's talk about the different types of wings a little bit. We have four main type of wings that we want to talk about. The rectangular wing, the unswept trapezoidal wings, swept wing, and the delta wing. Let's have a closer look at the swept wings. In the swept wing, we have a very important parameter called the sweep angle. The sweep angle causes definite changes to the maximum lift and changes also in the stall characteristics, as well as the compressibility of the wing. Sweep angle is a very important parameter in your supersonic condition. Is there anyone who can tell me what will be the difference? What will be the effect of sweep angle? That what will a higher sweep angle do to lift and drag, for example?
Pretty sure it minimizes drag.
How does it minimize that?
Does it changes the angle that the free stream air is hitting the wing, and it makes it like less perpendicular to it?
Okay, and how does that change your drag? What you said is completely correct. It changes that angle. So essentially, it is going to increase the effective length that air is going to be on the wing, right? Okay, but how does that decrease the drag? Because you're essentially increasing the shear, right? Your total shear force, because your air is going to be longer on your wing, right?
So if you're increasing the shear, then you're decreasing the normal force?
No, not necessarily related. You said it's going to decrease the drag. I didn't say it. I'm just trying to understand the phenomena better with you guys. So yeah. So that's what happens. It's gonna stay on your wing longer. But how is that related to decreasing your drag? or is it decreasing drag?
Does it have anything to do with the pressure drag of the turbulence after it rolls off the wing?
Pressure drag of the turbulence.
Like if the air stays on the wing longer, at least from leading edge to trailing edge, would that?
I assume what you want to say is that the flow separation will be delayed. Is that what you want to say?
Mm-hmm.
I don't know about that. I don't think it is something that may happen, right? But the flow separation happens because of a pressure like reversal, right? Pressure direction reversal. And I assume your drag is going to be increased because your pressure reversal for the same condition is going to happen at the same location, but you will have a higher length of reverse pressure at the trailing edge, right? Compared to the regular unswept wing. Does that make sense? Okay. Any other one of you guys want to jump in? Chime in?
So, more flat the geometry of the wing, you're gonna get more drag. And it's a more curvy geometry. A lot of the air is gonna be, instead of hitting it just flat in its face at 90 degrees, it's gonna curve around, it's gonna give it more lift. And that curvature would bring less drag because the air isn't hitting it at a flat angle.
I cannot make the connection between air is hitting something at a different angle and reduce drag. How do you make that connection?
So if the wing is flat, I don't know. I guess I can't really explain it anymore than that.
I mean, I think I know what you're getting at, where it has to do with how the wing is oriented to the oncoming air, and how much of the force is just going directly into the wing, and how much of it is deflecting off of it or being moved away by the airfoil.
Because if it's flat, the air is just going to try to push right through the wing. But if there's curvature, it's going to get directed to its edge instead of trying to push straight through the wing.
Okay, so essentially, what I assume what we want to say is that you're going to see less downwash.
Downwash?
You remember what downwash was? You haven't passed aerodynamics yet.
I did, but
You don't remember downwash. Did you cover downwash in your aerodynamics?
Oh, we did. It's just we didn't linger on it too long.
I remember him mentioning it,
He
but it
mentioned
was
it.
just a quick stop on it.
Huh. Okay, so but just forget that we were talking about downwash today. But so what I can so essentially your effective length in this direction is gonna be smaller, right? When you have a swept wing, right? And what does that mean? Is that you're effectively there is less in this direction, right? In the span direction, there is less wing in front of air, right? I assume that's what you wanted to get at, right?
that's it.
So your total drag is going to be smaller. Not the drag on the airfoils, but the total wing drag is going to be smaller because you have less wing that is resisting the air, right? Does that make sense? Okay. That's an acceptable explanation. Yeah.
So with the sub design, you also are lowering the distance, like the tips of the wings are from the fuselage. So since the lift is closer to the fuselage, how does that affect the full flight parameter?
Okay, that's a very good question. So is the lift closer to your fuselage with the swept wing?
I would say so. It's angled towards.
But the lift, you remember what was the lift distribution on the wing from your aerodynamics? It essentially goes from 0 to a maximum on the fuselage and to 0 again. Did you see that in your aerodynamics? Yeah. So essentially, since you have the minimal lift at the wing, I don't think you will see that much of an effect because of the lift distribution closer to your fuselage. But these are all design parameters. These are not set science, right? So you can play with them. You can do it like CFD analysis and see what's the effect of that. Does that make sense? Okay, so let's move on. And the other parameters that are very important are the wing area, S, that we have been talking about, wing span, V, which is measured from tip to tip, and the average chord that you are going to use in your analysis. This is the essentially wing span divided by your wing area. Are you writing or should I go to the next slide? Yes, go ahead and write. Go ahead, finish writing. Okay. One of the most important parameters, based on my experience actually, that is going to affect your flight, its effects are more obvious when you're flying a plane compared to other parameters, is the aspect ratio, right, of the span. We define the aspect ratio as your span divided by the chord length, right? But since the chord length is going to be different in different types of wings, we are going to use the span and the wing area. So B squared over S, your wing area. Yeah, it is very important in determining the structural. Let me actually ask you this. What do you think will be the effect of aspect ratio? Let's say, what is the difference between a high aspect ratio and low aspect ratio?
Well, I guess it's like the how long and thin a wing would be versus how short and stubby it would be. So I guess a glider would have a really high aspect ratio because it's got really long, thin wings, and something like an old interceptor.
But what is the effect of that thin thing? Why a glider has like high aspect ratio wings?
Probably high lift, low
High
drag.
lift.
High lift, low drag.
Okay. How would you get to high lift, low drag from aspect ratio?
So the aspect ratio is the span of the wing versus the chord length of the wing.
That's right.
So the higher the span is, the higher the aspect ratio is. So if the wing is spanned out more, that means it's wider and longer.
That's right.
So a wider and longer wing should be able to get more lift.
Okay. So let's. You're actually. The mistake you guys are making here is that you are convoluting the area with the aspect ratio. So you can actually have a very high aspect ratio and a low aspect ratio, both of them having the same area and generating the same lift, if you will, based on your logic, right? I mean, lift generation is going to be different, but from your logic, you can get there. So you can have two different aspect ratios giving you the same amount of lift, right? Because that's the area that is covered by the wing, right? So having a high aspect ratio doesn't necessarily mean having a very high wing area, right?
So that it's not area, it's length. Span.
It's the span versus chord length, right? Mm-hmm. High aspect ratio means that your span is much larger than your chord, right?
So then if your span is much larger than your chord, the air has to travel a smaller distance to go over the wing to be separated.
Mm-hmm.
So that would mean less drag.
Okay. I like how you're thinking, but okay. But it may, I don't know actually if it directly results in less drag. But the main contribution of high aspect ratio is more stability, right? Actually, one of the reasons is just what you just mentioned, is that you will have a smaller chance of flow separation and stall, right? Okay, so that's why in the commercial airliners you see that the wings are so long compared to the fighter jets, right? But because of that very long wings, like rolling the aircraft is going to be harder as well, right? So if you want to have a more maneuverable aircraft, you want to have a low aspect ratio. Like for a supersonic jet, fighter jet, we have an aspect ratio of 2. But for a glider, which is the aircraft that works based on the stability of your design, you want to have a very high aspect ratio, right? Glider doesn't have an engine to provide any thrust, so you want it to be as stable as possible and remain, yes.
So higher aspect ratio is more stability?
More stability. That's
So is it like comparing a dart to a paper airplane? Like if you threw a dart with spin, it would continue to spin, but if you threw a paper airplane with spin, it would kind of stable out.
I mean that's a logical. Yeah, that makes sense. That's a good example. Yeah. Okay, so moving on, some more definitions. CR is the root chord. T is the tip chord, and we also have the parameter of the taper ratio. Let me ask you this question. I mean, of course, the taper ratio affects the lift distribution and the structural weight of the wing. And what is the taper ratio for a rectangular wing? What is the taper ratio for this type of wing? 1, right? Because your root chord and your tip chord are the same. What is the taper ratio for a delta wing?
Be a half.
What? Half?
Yeah, I got that from like 1/2 base times height. That's where I got the number. Looks like a triangle.
It is a triangle. So what is the tip chord there in that triangle? These are the tip of the wings, right? What is the tip chord? Zero, right?
Yeah,
tip chord is 0.
If it's a point, yeah.
Yeah. So your taper ratio is going to be also 0.
Okay.
Right?
Yeah.
We also have another parameter called the mean aerodynamic core, which is mostly used in I want to say in a stability analysis. And you have to have the distribution of the chord variation versus the span, right? You want to have that function, and you just take the integral from negative half a span to positive half a span, which is also the one total span. And when we take that integral, we can find the mean aerodynamic core. And using that, we can, of course, use the moment of the aircraft wing, which is the primary parameter we are going to use in the stability analysis of the wing, right? Is there any questions so far? No? So let's move on. The wing location, as I mentioned, can be different. We can have high wing, where wing is located on top of the fuselage. We can have mid wing, where wing is located in the middle of the fuselage. We can have low wing, and we can have the parasol wing. It's mostly used in older designs. Okay. Another parameter that contributes to stability is the dihedral angle. We can have a positive angle here. Positive dihedral angle is called the dihedral design, and a negative dihedral angle is called the anhedral design. Dihedral angle is mostly used for just changing the stability characteristics and stability versus maneuverability. So whenever you want to have a more stable aircraft, you will lose some maneuverability, right? So more maneuverable aircraft will be less stable. That's why you will need a more a better pilot, right? To be able to. That's why for fighter jets you want to have the best pilot. compared to commercial airlines. And they actually affect the lateral stability of the aircraft. The lateral stability is the tendency of an aircraft to return to its original trim level. As an example, when you have a positive dihedral angle, which means that your wings are dihedral, when wing is hit, if the aircraft is hit by a wind gust, what's going to happen? And if, let's say, because of the wind gust, your aircraft rotates this way, you're going to have higher lift because of this angle on this wing compared to this wing, which will move the wing back to its location. But if you had an anhedral angle, the wing would have been different, right? The lift distribution would have been different, and then it would have been easier for the pilot to essentially roll the aircraft, right? So more maneuverable.
So I've noticed that some like large military cargo aircraft have an anhedral angle for their wings. Is that because they're too stable and can't make turns without an anhedral angle?
Cargo military. The thing is that most of them also have the top wings as well. So you have to go into their design and see what has happened. I haven't studied those designs, so I cannot answer you with like a high degree of certainty. But I would assume that they have that angle because they wanted to make it more maneuverable. Yeah. But I mean, you have to see the structural constraint as well. Like the weight on that. A lot of things play into designing a wing, right? Okay. Okay, we have two examples of dihedral and anhedral wings. Another parameter is the angle of twist, which essentially we can have two types of twist, the geometric twist, which means that the angle of attack of the root and tip are going to be different. So your wing is literally twisting, right, from the beginning to the end. We can have washout, which means that the angle of attack, which happens when the angle of attack at the tip is lower than the root, more common. And we can have wash in, which happens when the angle of attack at the tip larger than the root. I think we are spending a lot of time on this, but yeah, let's talk about this a little bit as well. So the idea here is that you have a higher angle of attack, like for washing, you're going to have a higher angle of attack at the tip compared to the root. Okay? Well, what's going to happen there? When you have higher angle of attack at the tip compared to the root, what is going to happen? Let's talk about this when we are talking about the sweep angle. We have let's talk about it in the next slide. We have the aerodynamic twist, which means that your airfoil is going to be different. Your airfoil shape is going to be different from the tip to the core. And we can also play with the sweep angle, as you have seen, right? We can have the forward sweep, which is a washing design. And we can have the regular common backward sweep. Backward sweep is more common. The first time the forward sweep was used, it was in the World War II by Germans in an airplane called Junker U-287 in the World War II, right? Okay. So is there anyone who can tell me what is the mechanism of the forward sweep that makes it more appropriate for like military aircrafts?
Maneuverability.
What's the benefit? Okay, maneuverability. How does that happen?
It's a lot less stable.
It is definitely a lot less stable, right? But the reason behind this maneuverability is that the stall, usually the flow separation, because of this washing phenomenon, happens near the root, right, near the body. So the ailerons usually stall later. When your ailerons stall later, it means that you can always play with it. I mean, they have installed, so you can easily roll the aircraft, right? Does it make sense? But there are other benefits to it as well. Reduced drag is one more benefit, but it is very unstable. This type of aircraft. That's why they haven't been used. I don't know if they have the forward tube design has ever been used outside of these two. It may have, but I just don't know about it.
It's part of like a counterintelligence thing. The U.S. did it to see if the Russians would copy it, and they did. So it's just kind of to see if like we were being,
Okay.
mold.
Okay. I didn't know that, but that's good to know. Okay, so what is the difference when you move from the airfoil to the wing, from two-dimensional design to the real wing? As we have mentioned, there's this phenomena happening. Is called the washout. Okay. Okay. And this is the washout phenomenon, essentially. We have high pressure at the lower side of the wing and low pressure at the upper surface of the wing, and that's the main reason behind your lift, right? But when you're dealing with a three-dimensional wing, what is going to happen at the tip is that there will be some leakage from the bottom surface, from the lower surface to the upper surface, right? From the sides of the wings, which effectively means that at the tip specifically, the pressure difference is going to be zero, right? Which means that at the tip, you are going to get zero lift, right? And as you go further in, closer to the fuselage, the effect of this leakage is going to diminish essentially, and you are going to get the maximum possible lift on the fuselage essentially. That's why the distribution of the lift looks like a parabola, right? Does that make sense? That this is the washout phenomena. This is what happens in the downwash. I'm using downwash.
So it causes vortices?
No, not the phenomena itself. The phenomena itself is not caused, but they actually this leakage. This is just a streamline. This is not a vortex yet. This is just a streamline from top to the bottom. Right? It's a circular streamline. It does look like a vortex flow, but the vortices are actually what happens when the flow leaves the wing, right? You're going to get wing tip vortices, right? That's what you see I mean, you should have seen wing tip vortices, right?
Yeah.
You don't know, right? Why did I say watch? That's the problems of not speaking your native language, guys. This happens a lot. Okay, so is there any questions here? Okay, so this was essentially the theory we wanted to cover. We spent a little longer than I expected, but that's all right. But what we want to do for this lab, for the upcoming lab, is to essentially analyze a specific airfoil or a couple of airfoils for different angles of attack. And what's going to happen in the lab, which is going to be here downstairs, is that we are going to essentially teach you how to use the code, how to use the software, and then you go home and choose a different airfoil and like run the simulation again, and then run your report, right? So that's the idea. But what we are going to do today is that we are going to use the software. We are essentially going to be going to see a small intro to the software, and yeah, we are going to use the X-Foil software. It is developed by Aerospace Computational Design Lab at MIT by Dr. Derella's group, Mark Derella, who is like one of the most famous people in aerodynamics. He's very old now. In the early 2000s, so this is a very old code, right? And it uses panel theory. If you end up taking a 500 level aerodynamics course, you will see what panel theory is, but you essentially have seen all of the theory for it in your aerodynamic one, the incompressible aerodynamics. Okay? But the hard thing about it is that it is a command line based program. So you don't have to write any code per se, but you have to know the commands. You have to know like 5 or 6 commands. That's it. That's the maximum. But let's see how it works. So what I'm gonna do is that I'm going to go and install it on my computer, which is very easy. It is not a very just go to Google X-Foil, first link, right? If you are running it, you can actually have different versions, the Linux or Unix version. You can have the Mac version is somewhere here as well. Yeah, the Mac version is the Mac version if you have a Mac computer. But all the computers we have in the lab are Windows computers, so we're gonna use this 6.99 software. Let me download it. Just extract the file. Pretty simple. Download. Then I just extract this. Oh. Okay. After extraction, there's no installation, so that's it. Just extract the file and that's it. And as I said, it is a command line based software. So you have the command line. The first thing you want to do is to you want to choose an airfoil, right? The airfoil used in the Cessna 172 aircraft is the Clark Y airfoil, right? For the most part. What you want to do is go to UIUC airfoil database. You know, UIUC is University of Illinois Urbana-Champaign. Right? They have one of the most comprehensive airfoil databases, and then you look for the airfoil that you want to have. Right? We are looking for the Clark Y airfoil. Clark Y. That's it. Download this. Let me just copy and paste it first. And we have to know a little bit about the data structure that is acceptable by X-Foil. We have to remove all of this file. And your data, so these numbers refer to the data points of an airfoil. So if you plot them, it will give you a complete Clark Y airfoil, okay? But they have to be structured in a way that first data point represents the trailing edge and then moves from the upper surface to the leading edge. As you can see, this is not how the data points are ordered here. They start from the leading edge, then go from the upper surface to the trailing edge. Does this make sense? Okay, the first number is 0, 0, your leading edge, right? Then the second number is 2 positive numbers, which means that you are moving on the upper surface from the leading edge to the trailing edge and back, right? Mm-hmm. We want to actually start from the trailing edge, go to the leading edge, and back. Does this make sense? Yeah?
So you're going in a counterclockwise motion?
Yeah. Okay. That's the idea.
That's going from leading to trailing back to leading?
No, from trailing to leading, from the upper surface back to leading. So your numbers must be ordered that way. Does this make sense? Okay. That's pretty easy for Excel to do. You essentially have to since we already start from the leading edge, go to trailing edge, we just have to change the ordering, right? And all of these chord lengths are normalized in the UI UC data plate. So they go from 0 to 1, always 0 to 1. All these are normalized, right? Okay, let's see, where was the ordering, editing here? Okay. Sort. You go to sort in Excel. I assume you know all this. Sort, we have from A to Z sorting already, so you just have to replace the sort. You see it starts from the trailing edge now, right? From x equals to 1, right? And goes to x equals to 0, right? And then it starts from the x equals to 0, which is the leading edge, goes from the bottom surface to the trailing edge again. Okay. And we can actually remove this as well. Then you save this as a text file. That's very important. It should be a text file in your Xfoil folder. Text MS-DOS. And let's call it Clark Y. You go to your command line and then just have to type the name of, because it is in the same folder, just have to type the name of your file, .txt. Okay, Clark Y. What's the Clark? This is a text file, right? Yeah. Let me just check this. Okay, it should be all right. Oh, I forgot the command load. It should be load from. Sorry. You do load clarky.txt. Yeah, and then you choose a name for the effort. Let's call it Clark Y again. It gives you the number of nodes you have for the effort, right? We have 122 points. You can increase this. You can decrease this. Let's increase the number of points to 400. 400 is not recognized. Okay, change one. Let's see this. This is essentially the number of nodes you see in here. This is the effort, right? So the orientation, the data structure, everything was correct. And if you want to change the number of anything, you just use the command p-par that as I have, and then it tells you the commands nptr xt whatever, right? You see those, right? And what those represent. Like the number of panel nodes is 160. If you want to change it, you just change n, for example, enter the number of panel nodes. Let's say 400. Let's see if this accepts 400 now. Okay, and then if you don't want to change anything else, you just click enter. That's it. So we have 400 nodes now. And if you do p-par again, you will see that the number of nodes are going to be higher. Okay.
So if you want to change the number of nodes, you type in P par, and then you type in N.
That's right. That's right. See the number N here is the number of panel nodes. Right now it is 400, but it was 160. If you want to change the trailing edge to leading edge ratio of the nodes, you just have to put T and then plug in value between 0 and 1, for example. If you do 1, it means that the concentration at the leading and trailing edge are going to be equal. Right now, we have more nodes at the leading edge, but you want to have that concentration to be equal, right? Because the trailing edge is also very important for us. This happens, right? Okay, so how can we run this? To run this, you just have to type oper, which stands for operation. Right now, you can see your xfoil command changed to oper I, which means that operation in the inverted condition. If you want to change it to viscous, you have to type VISC, right? If you, let's say you are doing it at a high Reynolds number, high Mach number, right? You want to do a viscous analysis. It asks you for a Reynolds number. All of these things are design parameters. Let's say you decide to analyze knockout 2412 in a specific altitude, right? At a specific Reynolds number, at a specific cruise speed or whatever, right? You have to calculate the Reynolds number and the Mach number, all of them, and you have to plug those in, right? So the predefined Mach number is 0. You don't need to change it, but if you want to have a more accurate analysis, of course you have to change it. And then number of iterations. Are you guys familiar with the iterative solutions in general? Do you have any idea what those are? That's it. What when I say iteration, what does it mean? So essentially, the panel method or any numerical method, what happens is you guess a solution, and based on that guess solution, you find a new solution, right? And if your new solution is very different from your guess solution, it means that you have a very high error, right? Then you have to use that new solution as the new guess, solve it again, right? Each step is called one iteration. Sometimes you may need 1,000 iteration, like 100 iteration to solve it, to get to a very specific, a small error, right? Does this make sense? So that's the iteration. The iteration is already set to 10 as a prescribed thing here. 10 iterations is usually very small to converge to an acceptable solution. So you want to change that iteration limit. I usually change it to 1,000. And so we are ready to run the simulation. Let's say we want to run it at the angle of attack 0 first. You want to run it at the range of angle of attack, alpha 0. That's it. It is running it now. Finished. And you get to see your results here in the other parameter. Here you see on the bottom, you see your airfoil, right? The yellow line represents the flow stream on top of the airfoil. As you can see in the alpha 0, in this Reynolds number, we don't have any flow separation, right? It looks like we don't have any flow separation, and the flow on the lower surface as well. We also have the CP as the yellow line on the upper surface, and the CP on the lower surface. Okay, just have to keep in mind that the CP variations goes from positive to negative, right? So, which means that you get your lowest pressures on the top surface, right? Your minimum is going to happen on the top surface, which is what you expected, okay? But what you want to extract from this result is this alpha, CL, and CD, and L over D, okay? And you eventually want to present the CL versus alpha, CD versus alpha, LD, L over D versus alpha, and the drag forward, right? So to be able to have that, you have to run your simulation for a host of different angles of attack, right? So we have the result. You have to record the result manually, like CL for alpha 0 was this, CD was this, whatever, in Excel file, whatever you want to do, right? And then you initialize your solution again. So you go back to the 0 solution with this command init, okay, which means that your boundary layers are going to be initialized. And then let's do alpha -1 this time, which means that -1 degrees angle of attack. Okay, your CL has changed, your CD has changed, L over D, and so on and so forth. Okay, let's see what's going to happen to our results if we do alpha 20. Initialize again, alpha 20. So 20 degrees angle of attack for a Clark-Wall airfoil. So, what do you think has happened here?
So the laminar flow separation happened a lot earlier on the way.
Laminar flow has separated, right? Which means that you have, it looks like you have a leading edge separation, flow separation. So flow is separating from here, which means that you are well into the stall condition, right? So you have already passed the maximum CL range. So the CL you're going to see here must be smaller than the lower angles of attack. So to make sure that's the correct conclusion, you want to run alpha 15, for example.
All it took was just 20 degrees to have a stall condition.
20 degrees is very high, actually. So your stall condition in a real world solution, your stall condition usually happens at 7-8 degrees with these airfoils. Okay.
What kind of airfoil is this?
That's it is a very good airfoil. It's not a bad airfoil. But yeah, let's do 12 degrees. The CL was 1.3, right?
Yes.
So let's do alpha 12 and see what are we gonna get. See, we are getting a higher lift coefficient with a lower angle of attack, 1.45. Okay, which means that we don't know if this is the maximum. So if this is a stall angle, we have to run some more simulation to find the stall angle. But with 12 degrees, we are getting a higher lift coefficient compared to the 20 degrees. Okay. Is there any questions? So this is what you are going to do in the lab. You're going to choose you're going to use the Clark-Y airfoil. You're going to restructure the data so that it's acceptable by the Xfoil software. You're going to find the CL versus alpha in the lab, and then when you get home, you have to try it for another airfoil as well. Do the same thing for another, and then write your lab report. Okay. And we are going to finish by talking a little bit about curve fitting. Have you guys passed any statistics course? 509. Yep. So you are already pretty familiar with the regression analysis and curve fitting and stuff, right? Yes? Okay. Yes. So I'm gonna be quick as much as possible. Essentially, you can present your data that you read from the experimental measurements or numerical measurements using a table, text, or graphical. In the engineering analysis, we usually use the tabular presentation or the graphical presentation. But what you get from experimental or numerical measurements are going to be a couple of separated data points, right? And how you present those data points is very important, right? You want to be able to find a function to represent your data point, right? Because it's going to be easier compared to a table, and it is. You can actually extend that function to to the points that you haven't really measured, right? For example, you cannot really say anything about the value 2.5 here. What's the value? The value may be here. Maybe give you a 60, right? Because you don't know that, right? But with curve fitting and interpolation, essentially, it will give you a good idea of what that value may be. Okay, most probably what the value may be. You may be all wrong, but that's the best you can do, right? So that's the idea of the curve fitting. I'm pretty sure you're familiar with the curve fitting. It's essentially what you do with the curve fitting is that you find a correlation for your data between x and y. And we have different types of correlations. We can have a straight line, we can have a parabola, we can have the polynomial correlations and exponential. But most common correlation used in, especially in social sciences, is linear correlation because that helps us explain everything in an easier way. Not the best way usually, but easier way definitely. The method we are going to use, you are going to use if you were to find if you were to do a curve fitting. You of course use Excel or whatever. You don't do this by hand. But if you were to do it by hand, you should use the method of least squares. And how you do that? Essentially, what you do is that this is the main function of the least squares method, right? So you have a measure value of yi, and let's say you want to find the linear correlation for your data. You have the equation of a law, ax plus b, right? Yi and xi are the value measured by your experiment, and what you want to find here is a and b, right? Those coefficients, right? So the way to do this using the least square method is to minimize this function. How would you minimize this function? We already know that. You just have to take the derivative with respect to a, one of the variables, and also with respect to b, and set them both equal to 0. You can actually do it simply for this case. You can do it by hand, but if you were to deal with a polynomial, it would be, of course, a little more complicated. So if you take a derivative with respect to a and b until it equals to 0, you can find final values for a and b. And this is how a machine actually gives you the best correlation. It takes all the measurements, does the summation, and puts it in this equation, and gives you the coefficients for a line that will fit your data. But this is not the final thing you need to do when you are finding a correlation. You just have to make sure that correlation really represents your data. That's why you have to find the regression, right? If your regression is very high, are you guys familiar with regression? I'm pretty sure you are, right? So what is the maximum value a regression can have?
1.
1. Okay. What does a 1 regression mean?
So
That means it's the highest correlation.
It's the best fit, essentially, right? Exactly. So why is that? The main formula for regression is 1 minus the standard deviation of your from the average of your data, right? The standard deviation from the average, and also the standard deviation, if you want to call it the standard deviation, from the function that you have chosen, right? Just compare the two value. If the standard deviation here was 0, essentially, you're going to get r is equals to 1, which means that you have the best fit. Okay, you always have to calculate the relation, and let's do a rule of thumb here. You always want to plot the data to obtain a visual observation before performing any analysis. That's actually pretty important, right? Let's say, because if you don't visualize the data, you may actually do it all wrong, right? Let's say you may have this type of data, right? If you don't plot this, if you don't see this, and if you just do the calculations, you will definitely be able to find a correlation with it. with a good regression, actually, with an acceptable regression like 0.4, 0.5, right? With a 0.4, 0.5 is very good, actually, right? But it is a terrible correlation because your data are obviously not related to each other. They are not correlated to each other, right? So visualization is very, very important. That's the point. And then consider taking out the outliers, if you will, and plot the both of them with the fit curve, do a regression analysis, and never accept the least square analysis only based on calculations. Okay, so that's it. That's all of the lecture we are gonna have for today and this week, essentially. And yeah, let me know if you guys have any questions or concerns. And I'm gonna see you guys in the lab.